So what that means is, therefore, is that the actual amount of force is less than required. And we learned that when the actual amount of force pulling towards the center of a circle is more than is not as big as what you need, what happens? Do you fly out or fall in? Fly out into a bigger radius turn. Okay. So here, you need more force than you get force. So therefore, you fly out into a larger circle. You basically find the radius at which you find the balance point between what you get and what you need. Okay? So that's a very useful formula in and of itself. It's the radius of the circle made by a charged particle in a magnetic field. Okay. I forgot, before I forget, I should mention that the positive charge is what obeys the right-hand rule. For a negative charge, as you can probably imagine, it always does the opposite thing. So let me give you two strategies of how you might attack a negative charge. The first of which is to pretend it's positive and then reverse your answer. So right-hand rule, and then reverse your answer. So as an example, if you threw in a positive charge here, or sorry, a negative charge here, we could do the right-hand rule. We could slap B into B, so like that. We get the forces to the left, just like we found over here. But then we say, oh, it's negative. It's actually this way. And so we find that it actually circles around the other way. So from our perspective, in that diagram, the positive charge would make a counterclockwise circle, but the negative charge would go clockwise. Again, not a surprise. Negative does the opposite of a positive. So that's your first option. Or we can leverage the fact that we pointed out all the reasons why you shouldn't use the left-hand rule now are good reasons to use it. Remember, it gives the opposite answer. So if you do the left-hand rule, you get the opposite answer. Now that's a good thing. So you can try that if you want to. Use your left hand, slap B into B, forces like that. So you can think of it as positive charges are right-handed and negative charges are left-handed. So what does that mean? Don't really have little hands or anything like that. What it means is that the mnemonics that we've come up with, one you use your right hand, one you use your left hand. Okay. The only thing to caution you, use option 1 or option 2, don't mix them up. If you do the left-hand rule and then reverse the answer, you're back to the same answer as the right-hand rule. Okay? So use either 1 or 2. Don't have a double negative. Don't use the left-hand rule and reverse it, because then you're back to the right-hand rule answer. Okay. So the only other thing we need to establish is we've talked about what happens with something. What do we do with something like this? So what I want to do here is I want to catalog all the possible motions of a charged particle in a magnetic field. So the type of motion that we have, I guess let me do this. Do we have B parallel? Do we have B perpendicular? What is the motion like? So let's make a little chart. So let's knock out the very simplest cases where nothing happens, there's no force. If you don't have either type of velocity, of course, that means you're at rest, and you stay that way. If you have just B parallel but no B perpendicular, well, remember that B perpendicular is where the action is. That's where the force comes from. So you the force comes from having this. The force comes from having a yes answer in this column, okay? So if you don't have V perpendicular, you just have V parallel, what's your motion going to be like? You're just going to have a constant velocity either with or against the field line. That's a net force of 0. So that's these cases right here, okay? So now we get to the stuff that's exciting, where something actually happens besides Newton's first law. So these are just Newton's first law. The case we just did is we had V perpendicular, but we did not have any V parallel. Well, then what you will do is a circle, circular motion, and the radius of that circle will be r equals mb over qb. So, obviously, our final case, what if you have both? So what if it's a yes and a yes? Well, that is simply just going to be a combination of the previous two rows. So you're going to have circular motion and motion with or against the field line. Okay? So you will be circulating, but you will also be drifting. So for instance, here we not only have V perpendicular, but we have V parallel. So you're also going to just go at a constant velocity downstream. So what happens if you were going in a circle but also had a drift like this? What kind of motion are you going to make? It's a spiral or a helix, right? So here you're going to get a helical motion. The helical motion, the radius is determined by only V perpendicular. Remember, that's the only thing that participates in the magnetic force existing at all. Now that right there is a little sleight of hand. I just replaced V with V perpendicular. If you were deriving yourself, you've got to be careful. Here's what I recommend. You say FB equals mv squared over r, but you've got to be really careful. Here's why. This is full 3D motion. And full 3D motion means that the velocity can have both an x and a y and a z component. And we haven't talked about it at all. So even though this velocity here, it has both an x and y component, as you might say, that's still not the whole thing. There still could be a component into or out of the page. So the component that's relevant here is not actually the entire V anymore, right? If you're going in a helix, you have only a component, the V perpendicular, that's circulating, and you have another component, V parallel, that has nothing to do with any of that. Okay? So if you solve this, you'll get this. Common mistake is to put in V here as if it's the entire speed. But remember, when you're going in a helix, there's a part of the motion, V parallel, that has nothing to do with the circling. Okay? So that helical motion is you still make a circle, and you also have what I'll call the drift. The drift. And there, because that's just Newton's first law, you just basically use distance equals rate times time. So the whatever parallel component you have, you just truck along at a constant rate. You can truck along downstream or upstream to the field. It doesn't really matter. The magnetic field could care less about that. Remember, it's latching onto that perpendicular component to cause the circling. But you can spiral. If, for instance, this right here, if this was V perpendicular, this is the component that's perpendicular to the field. We could also have a parallel component that was into the page, then it would spiral like this. Or if we happen to have a parallel component out, we could spiral like this. So you could go like this, or you could go like this. It doesn't matter, right? Because remember that this part, the magnetic field doesn't care about. You can go downstream or upstream. That's just how you threw it in there. And even if you throw something in like this, the parallel part just does what it does. it's this part that gets picked up on and caused to go in a circle, deflected into a circle. So those are the possible motions of a charged particle in a magnetic field. Are there any questions on that? Okay, so once we have this, we can build up everything else we want from this. We're going to first take not just one charged particle, but a bunch of charged particles in a current. So you can have a magnetic field affecting a current. It can literally pick up a wire that has current in it. So that we'll do next. And then what we'll do is we'll take that current and we'll cause it to go in a circle. So we'll look at the effect on a current loop. All right? So let's see if we can get done with that. That'll close out homework 5. So I think we have a shot at it. See what we can do. So this is a force on a current carrying wire. The current is going to be I, and it's going to have a length L. So for instance, let's say we have a magnetic field like this. We have a wire with current going down it. Well, what is current really? Current is the motion of positive charges. Let's say we take a look at a segment of length L. Now obviously current can't just come out of nowhere, flow L, and then disappear. So this might be a segment of a larger circuit or something like that. So let's work it out. All I'm going to do is I'm going to grab the QV out of here. So Q times V. And then I'm going to take the QV and I'm going to put that V is the length of the wire divided by the time it takes to travel it. Okay? Is that cool? Right, so the speed is length per time. And then all I'm going to do is I'm going to take that time and I'm going to steal it for the Q. I'm going to group these together. So instead of talking about the length per time, I can talk about how much charge traversed across in this time. We have a name for that. What's charge per time? Current. So all we have to do in our formula is replace Q times V with I times L, and we're good to go. So here's my new formula. FB equals ILB sine of theta. And I'm done. This is nice because I don't have to go down to the individual charge carrier level, right? I can talk about the current, which is the motion of lots of charges. L is the length of my piece of wire. B is the magnetic field it sits in. And then sine, it's always sine. And then the theta before used to be the angle between V and B. Now, of course, rather than saying the direction of the individual V's, let's just say it's the direction of the current. So here's our new formula. That's the size of the force. And the right-hand rule is exactly the same. Because what is current after all but the motion of a bunch of positive charges? So you can try it yourself. I slapped into B, right? So I points to the right, slap it into B, the force will be up. So this wire will get lifted up. Okay? This is, in fact, it's just the same right-hand rule. You might even say it's actually easier. You might say it's easier because there's no such thing as negative current, right? We have both positive and negative charges, but we never say that a current is made out of negative charge carriers, right? Current is understood to be the hypothetical flow of positive charge to lower voltage. Now, this is a case where you can say, we know that that's totally not right. We know that it's really electrons flowing the other way. Well, I welcome you. Let's try it. We'll slap B of the actual electrons into B. Force is down, but it's a negative charge, so it's up. So again, no penalty. No penalty for assuming that charge carriers are positive going to the right when it's really negatives going to the left. We'll find maybe one circumstance where it gives us the wrong answer, okay? So we continue with this charade that current is made out of positive charges seeking lower voltage. All right, that's basically one little kind of tweak, and we're good to go with whole sections of motions of charged particles, current carrying wires. Now let's take our current carrying wires and make them in a loop. So we have a current loop. I'm going to talk about a current loop. And I'm going to put it in a uniform magnetic field once again. And let me draw a nice rectangular loop with current flowing down all four sides. So current, 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 current. Of course, it's the same current circulating around, so it'd be silly to label them I1, 2, 3, and 4. That's just the same current going around and around. More practice with the right-hand rule. Let's try it. I'll do the top one first. Slap I, which points to the right, into B. Forces up. All right. Let's go to the bottom segment. Let's do them in matched pairs across from the rectangle. So I point my fingers to the left along with I, then I rotate my palm so that I can slap I into B. Forces down. What happens to those two forces? They cancel, that's right. Same current, same length, it's a rectangle. They're in the same magnetic field. That's key, right? If the magnetic field was stronger on the top versus the bottom, they would not cancel, right? But since it is a uniform field, they will cancel, okay? If you do the right and left segments, same thing happens. I slapped into B, we get this. Now don't get me wrong, this is a stronger force. Why is that force stronger than the top and bottom? The length is longer, exactly. It's not because it's the different current, it's not a different field, but the length is longer, but it's a rectangle. It has, if you want a current loop to connect up, it's going to have to be equally long on the other side. So what we have is that the pairs of forces cancel. Those go away. The net force is 0. The net force is 0 on a current loop in a uniform field. Now, I know that I've proven this to you only for a rectangle. This loop can be shaped however you want, and the result is general. Here's why. If you had some crazy current loop that looked like this, any crazy loop like that could essentially be grouped into basically a bunch of different rectangles. So whatever segment, let's say you had a segment over here where current was flowing one way, you'd have another segment over here where it's flowing the other way. So it's a general result. So in calculus, you can do things like this and turn continuous curves into stair steppers. We're not going to do that, so I'm just going to tell you that's the answer. As long as the field is uniform, the forces on the matched sides are going to cancel. This, by the way, is not the first time we've seen this. We saw this with electric fields. Remember we had a uniform electric field, and we put in a neutral insulator. You probably should be studying this, right? Minus, 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 plus, plus, plus. We did see that this minus charge, it got pulled to the left side, and it'll continue to be pulled upstream. This positive charge got pulled downstream. But what happened with the net force? What's the net force on that thing? They cancel, right? This cancels with this. They're the same amount of charge sitting in the same field, right? Now that's not to be mistaken for if you have a non-uniform field, you'll still have charge polarization, right? You will still have that the negative charge feels a force to the this way, and this positive charge feels a force to the right, but those won't cancel. That's because of the non-uniformity of the field, right? What's the direction of the net force? The net force points to the left, and so the net force is into the region of stronger field. If the field is non-uniform, the net force will be into the region of stronger field, but of course up here, there is no stronger field to be pulled into. It's all uniform. By the way, over here, what might cause this? This might be caused by a charged particle or a charged object, right? So this was why we found that neutral objects can be attracted by charged ones, right? That's the case here too. I think there's going to be at least one question on your homework. I don't remember if it's the next homework or the one after that. But I do stick this in a non-uniform field. Then there is a net force, okay? So likewise, like we learned over here, if there's a non-uniform external field, the net force is into stronger field. That is actually the same thing that happens with magnetic fields, okay? So if there's a non-uniform field, then the net force is towards stronger field. So that's one thing at a time, right? So we want to not make, not quite go there yet. Right now, there's enough interesting things that can happen with just the current loop in a uniform magnetic field. Now you might look at that and go, that doesn't seem very interesting. It just seems like it sits there. The net force is 0. And it does, it just stays there. However, let me show you what happens if you change the orientation a little bit. So what I'm going to do over here is I'm going to put the uniform field in. I'm going to have the uniform field point to the right instead of into the page. And then my current loop, so this thing right here is a current loop. And this thing right here, I want to actually draw from the side view, okay? So the side view means that you have to kind of get creative with how you draw the circulation. So this current that goes this way, this goes this way, and this one that goes this way, we can draw it from the side view. I draw it as coming out, so you see that there's a circle dot. I draw it going across, and then I draw it going in. And if I draw from the side view, I'm basically going to have to skip to the force side, the back side. So at least from the edge view, I can at least draw 3 out of 4 things. That's not bad. So I'm going to draw that here. Okay? I do that. I have current going out, going across, and then going in, and fourth side not depicted. So let's try the right-hand rule. Let me pick the current coming out first. So I point my fingers out. I want to orient my palm such that I can push I, which points out, into B, which points to the right. So out, slapped into right. The force is up. Okay, so slap up. Okay, so I draw that in. Here's my force. You can convince yourself that if all you do is reverse the current, the force will be reversed. Or try it again from scratch using the right-hand rule. Slap I to B. Tricky. what would be the force on this current from this magnetic field? Can't slap I into B because this I already points with B. What happens then? Remember, the charges are all flowing parallel to the field. Right? So if they're just flowing parallel, there is no force. So the force on the front is nothing. And the force on the back segment, those charges are flowing exactly opposite to the field, so their force is also nothing. So of course we have a net force of nothing at all. Okay? So you look at that thing and you go, all right, the net force does indeed seem to be 0. Okay? I have 2 out of the 4 sides of the loop, 2 are 0 already, and then the other 2, they cancel, right? One's up and one's down. So is this thing just going to sit there?